Certain morphisms in a category are given specific names when they satisfy certain properties. The first one that we'll look at is called an epoch. So a morphism F from A to B in a category C is called epoch if for any object C and any two morphisms going from B to C, call them G and H, we have that F is right cancelable. The sets in the diagram at the bottom provide a specific counterexample to this definition. That is, we have a single morphism going from set A to set B, called F, and two morphisms going from B to C, called H and G, where G after F is equal to H after F, since both of these elements map to the same element in B, and that element maps to the same element in C by both G and H. However, G is not equal to H in this case because there's an element here in B, not in the range of F, which assigns something different by G and H to this same element in B. On the other hand, if F were a surjective function, that is, say F mapped this top element to the other element in B, thus covering all of the elements in B in the range of F, it would be impossible for this property not to be satisfied. That is, there is no element outside the range of F for us to assign something different to from H than from G. This shows that non-surjective functions do not satisfy this property, while surjective functions do satisfy this property. That means that when the morphisms that we are concerned about are set functions, that epoch morphisms correspond exactly to surjective functions. Conversely, a morphism F from A to B in a category C is called monic if for all objects C in C and morphisms G and H, which both go from object C to object A, we have that F is left cancelable. Again, in the diagram at the bottom, we have a specific counterexample to this definition in sets, where F after G is equal to F after H, but G is not equal to H. Because in this case, although the singleton element in C maps to two different elements in A by G and H respectively, those two distinct elements in A then get mapped to by F back to the same element in B. And therefore, although the compositions of these functions are equal, the initial functions coming out of C are not equal. Notice that here we see that F is not an injective function. For F to be injective, every element of the codomain B could only be mapped to by at most one element of the domain A. However, here we have two distinct elements of A, both being mapped to the same element in B. Therefore, F is not injective. However, if F were injective, notice that this property would then always be satisfied, because we would never be able to have this expanding and collapsing pattern when doing composition. All of these morphisms would line up one to one, and each chain of composition would either be the same or it would be distinct, and therefore this property would always be satisfied by injective functions. What this means is that non-injective functions are not monic, while injective functions are monic, and therefore we can say that monic morphisms in a category, when we are talking about categories which involve sets, correspond exactly to injective functions. Next, we'll look at right and left invertible morphisms. So a morphism F from A to B is called right invertible if there exists a right inverse, that is a morphism from B to A, call it FR to the negative 1, such that F composed with its right inverse is equal to the identity morphism on B. And similarly, a morphism F from A to B is called left invertible if there is a left inverse morphism FL to the negative 1 from B to A, such that the left inverse composed with F gives us the identity morphism on A. Based on these definitions, there are a couple of results that we can show right away. The first is that right-invertible implies epic. So suppose F from A to B is right-invertible. Then take morphisms G and H, both going from B to C for any C. Then if G after F is equal to H after F, this implies G after F right inverse is equal to H after F right inverse. These cancel to 1b, which gives us G after 1b is equal to H after 1b, which gives us that G is equal to H. And that shows that F is in fact epic, QED. The next result is very similar, showing that left-invertible implies Monic. So suppose F from A to B is left-invertible this time. Then take any G and H, both going from C to A, for all C and C. And if F after H is equal to F after G, then that means F left inverse after F after H is equal to F left inverse after F after G. These collapse to 1A, which is 1A after H equals 1A after G, which shows that H is equal to G, similarly showing that left-invertible morphisms are monic. The next result will lead us directly into our next definition. So if a morphism F from A to B has both a left inverse and a right inverse, then the two inverses are equal and unique. So to see that they're equal, first notice that FR to the minus 1 is equal to FR to the minus 1 composed with the identity morphism on B, which is equal to FR to the minus 1 after, well, we can expand the identity morphism into F after its left inverse. But then these two can now cancel back to 1A, and we get 1A composed with FL to the minus 1 is equal to the left inverse. And so we have that the right inverse is equal to the left inverse. It's important to note here that not every morphism will have both a left and right inverse. But when they do, since they're equal, we can drop the subscripts and simply call that inverse f to the minus 1, or f inverse. Now, to see that that morphism is unique, suppose we had some other morphism, G, going from B to A, which was also an inverse of f. Well then, G would be equal to 1A composed with G, as always, but then the 1A we could expand to be f inverse after f after G, but then the f and the G would cancel and give us 1B, so we would have f inverse. So here we see that the two inverses would be equal, and that means that the inverse for any f must be unique. This result leads us right into our last definition involving special types of morphisms in a category. So when f from A to B has an inverse, which, as we have seen, must be unique and a left and right inverse, we say that f is an isomorphism, and we say that objects A and B are isomorphic. So any two objects which have an isomorphism between them are isomorphic in the category. One important thing to note is what happens when we compose isomorphisms. So suppose we have f from A to B and G from B to C, which are both isomorphisms. Then of course we can compose those two to give us G after F. And let's try composing both of those with F inverse after G inverse. Well, of course, composition is associative, so we could ignore the parentheses and cancel this to be 1B. That will give us G after G inverse, which will collapse to give us 1C. And now let's try the same on the other side. F inverse after G inverse after G after F. Well, of course, we can ignore the parentheses again. Here we get 1B, which gives us F inverse after F, which collapses to 1A. But then we've satisfied the definition of an inverse. Notice that when we composed F inverse after G inverse on the right to G after F, we got 1C, and on the left we got 1A, which means that G after F, which goes from A to C, is an isomorphism, and the inverse of G after F is F inverse after G inverse. We'll conclude with one more observation, translating back to the language of sets and set-like objects. So we've just seen that an isomorphism is a morphism which is both left-invertible and right-invertible. We also saw that left-invertible morphisms must be monic, and that right-invertible morphisms must be epic. We also saw that monic morphisms correspond exactly to injective functions when we're working with sets, and that epic morphisms correspond exactly to surjective functions when we're dealing with sets. But what is a set function which is both injective and surjective? Well, it's a bijection. And so this shows that isomorphisms in the category of sets correspond exactly to bijections between sets. And moreover, if we start talking about other set-like objects but add some more structure, say like a group, for example, well, now we have a group homomorphism which is a bijection. What is a group homomorphism which is a bijection? It's a group isomorphism. And so we can see that the concept of isomorphism in a category and the concept of isomorphism in other algebraic structures lines up exactly.